Hey there, awesome physics students. Let's talk about magnetic forces. Specifically, we want to talk about the force that a charge, an electric charge, feels in the presence of a magnetic field B. And remember, those magnetic fields that we're talking about are different than the electric fields. So let's start with an example here. Imagine I have a magnetic field, and that points straight down like this. And remember that B is different than the electric field. And I'm going to put a positive electric charge in here, a positive Q. And this is just a regular old electric charge, not a north pole of a magnet. Now if I put this in the magnetic field and it does not have a velocity, it's sitting there at rest, it will not feel a force. What I need to do to get it to feel some force is to give it some velocity. So I'm going to give it some velocity v in that direction. And you might think, well, then the force is going to point along the magnetic field line. But that is not how magnetic fields work. They're a bit more complicated than electric fields. The way to figure out the direction that the force is on this charge is you have to use the right-hand rule. So you take your right hand and you point your fingers along the direction of the velocity for positive charges. And then you push your fingers in the direction of the magnetic field. So that would be down like this. And then your thumb here points in the direction of the force. So that's going to be back into the screen. Okay, so the force is going to point into the screen, away from your face. And in fact, if you think, well, this seems familiar, it seems like we've done something like this before. In fact, it is a cross product. So it's the cross product of QV and the magnetic field. And so if you recall properties of the cross product, we're multiplying parts of these two vectors that are perpendicular to each other. That in turn gives us a resultant, that's the force, that is perpendicular to both original vectors. So the force here is going to be perpendicular to both V and B both. All right, so that's why you have to use the right-hand rule. It's because it's a cross product. Let's do an example with negative charges. So let's imagine that we have a magnetic field that points into the screen like this. So it points back this way. That's my magnetic field B. And let's give me a negative charge, and I'm going to have that have a velocity this way. Now let's look at this. Notice that when I take V, V points this way, but if I multiply that by Q, Q in this case is negative. So what's that going to do to that vector? It's going to flip the direction of the vector. So yes, V points this way, but QV, that points this way. So you have to think about the direction of QV. So again, you take your right hand, point your fingers of your right hand in the direction of QV, and then B is back into the screen. So I'll push my fingers into B, and then my thumb points in the direction of the force. The force in this case is directly up. And again, this force is going to be perpendicular to both the magnetic field and the velocity vector. All right. Finally, let's do an example where you have a magnetic field and the charge is moving parallel to the magnetic field. So here's my magnetic field B. The velocity of the charge is parallel to B. What do you get? Well, remember the properties of your cross product. The cross product is multiplying the parts of these two vectors that are perpendicular to each other. But these are parallel. No part of these are perpendicular to each other. So the result you're going to get is 0 because they're completely parallel to each other. All right? So hopefully this helps you understand what the forces on magnetic forces on charged particles are. It's a cross product. You want to think about put your fingers in the direction of the vector QV and then push it into B, and your thumb will give you the direction of the force. All right? See ya.